In the previous lecture, we had an introduction to noise and sound, and in particular regarding the sound pressure level in decibels, and then how to add decibels, and then what happens when for a spherical source or for a point source in 3 dimensions, how the SPL reduces by 6 decibels for every doubling of the distance. Okay. And then we did discuss about certain conditions as to the fields of noise: far field, free field, and reverberant field, etc. See, when I have a noise source, okay, it is radiating in all directions, the sound. But what happens once it comes to a boundary because of reflections? And if you see here, with every doubling of the distance, the sound pressure level will decrease, and then as you come close to the boundary, this is going to increase. Okay. And here also there will be some laws. So the region where the sound pressure level follows the rule that for every doubling the distance, the sound pressure level will decrease by 6 decibels. Okay. Now, but when you come close to the boundary, there will be an increase, and this is what is known as the reverberant field. And very near to the surface, this is the near field. So when you are doing a noise monitoring of a machine, it is good that we always do the measurements in the free field. But in reality, when I am talking about noise monitoring in machines, okay, in reality what happens, we will have many obstacles. Okay. So if you want to find out the noise radiated by a machine, it is ideal to put it in a free field environment. A good example of free field is an open field, like a large football field. You are in the center of the field where you are doing measurements, or in chambers which are specially constructed with wedges. Towards the end of the previous class, I was showing you a picture of a car in an hemianechoic chamber. These are all absorbing wedges. Such chambers are known as anechoic chambers. That means no echo. That means no reflections from the boundary. So the reverberation effects are not there, and everything which is going out will not get reflected back. So I can have my machine whose SPL I am going to measure at some distance by an instrument like a microphone. I measure in a free field environment. The reason why this is important from a CBM point of view is if a machine is producing noise and if I measure it in any other environment when it is not free field, the environment is going to contaminate the levels of produced by this machine. So, but in practice, in real world, in machine shops or in factories, it is difficult to get this free field environment for doing any measurements. Another thing we must have realized that when I add to SPL1 as maybe 10, maybe 40 decibels, say, if SPL2 is something less than 30 decibel, my net effect would be only 40 point something, 1-2 decibel. So, if the in noise monitoring, this is very, very important that the background noise must be more than 10 dB less from the SPL of the source which is being measured. So, that means if you are doing noise monitoring of a machine, suppose the machine itself produces 40 decibels and with the machine off, we must see that the background is less than 30 decibels. So, in effect the background is not going to affect the overall level or add to the overall level of the measurements. So, this is a very, very important rule which every noise control engineer follows when they have to measure the noise produced by machines for monitoring purposes. Okay. So, this is one thing which one has to very, very careful while you measure this SPL. By the way, just to let you know, SPL is measured in an instrument known as an SLM, that is sound level meter. Okay. So, as you see here, the frequencies which human being hear are from 20 hertz to 20,000 hertz. Beyond 20,000 hertz we have the ultrasonic noise, and below 20 hertz we have the infrasonic noise. But as you will realize, God has made our ears, and our ear is highly nonlinear. It is not a linear instrument. If I had a microphone with frequency, the frequency response of the microphone would be something like this, flat till its resonant frequency Fn, and we say this is the useful frequency range, and dB scale output by input is 1. So, this is 0 decibel. Okay. But our human ear, this is for an FRF, frequency response of an instrument like say a microphone. Our human ear is not like this. Okay. So, we will see the mechanism of human hearing. So, this is the outer ear. Okay, we have the ear canal here, and this is this ear drum. So, ear drum is actually a very thin membrane which is subjected to this fluctuating pressure P, and then there are this series of 3 bones, and then we have an tube, and then there are certain hair cells which will deflect based on the sound pressure being transmitted, and then we will have neurons attached to it to give us a sensation of hearing. So everything from the outside world is actually incident with pressure waves on this eardrum, and then depending on how good your hearing is, some can hear for high frequencies, some will lose hearing because these hair cells get damaged, some could get permanently damaged and so on. We will not go into the details of this, but prolonged exposure to a high level could damage your inner ear and the cells, and which is not repairable. So that is the reason when we have noise all around us, one has to be careful that our ears, which has been given by the gift to us by God, are well protected. They do not get into a permanent damage mode. So people today are talking about noise pollution in transportation systems, in the railways, in the automobiles, in aircrafts. We are talking about machinery noise being loud, construction equipment. Of course, in our country like India, we talk about firecrackers during Diwali festivals and so on. So there are certain standards given by the Central Pollution Control Board of our country, and these standards one can refer to in the CPCB website or their guidelines, that some of the rules are there since 89, 2003, etc., etc. So these towards the end represent the year in which they have come into existence. So just for fan noise control, okay, I will just show you that we have 4 zones here, which is known as the industrial area, commercial area, residential area, silence zone. What is the equivalent time? I will come to this A weighting just in a little bit. What is the overall level to which the sound level should be? In a residential area in the night time, it should be somewhere around 45 or less. Okay. And because why do we have this? Because this is going to set in a permanent damage to our hearing and prolonged exposure. So one has to be careful about this. But in CBM, we are talking about noise control or noise monitoring as a means to monitor the health of a machine, or as a means to find out which area of the machine is making more noise. And to do that, there is a technique called noise source identification and ranking. By the way, I must tell the students here that though this is a course on machinery fault diagnosis and signal processing, the reason I am taking these 2 classes on noise and noise monitoring is for the fact that noise and vibration go hand in hand, and this noise will from a machine will draw our attention to that machine. So a little background about SPL, and then we will see about noise source identification and ranking. By the way, those of you who want to know more about acoustics and industrial noise control, we also have about 20 hours of lectures under the Gyan program on the same topic, and the details about them can be found in my website iitnoise.com. And if you go to the resources, web resources, you will see the links to this acoustics and noise control, and also for a previous lecture, 40 lectures on NPTEL on machinery, fault diagnostics and signal processing. Okay. So just if you want to have more information about acoustics and noise control, you can refer to my website and see our Gyan program, where we have about 20-hour lectures on acoustics and industrial noise control. Now, this is how a plant noise monitoring is done. The microphone is put on a tripod, and there are certain standards of noise monitoring, and that is typically the standard says you have to at a distance. This distance is specified usually 1 meter, and then this is my machine in a free field environment, and this is about somewhere about 1.2 meter, and this is your SLM, and this is your source. Okay. And then we can you have to measure the SPL in dB, or dBA is something which I am going to come to, and of course the background noise should be background noise must be greater than 10 dB below the actual level of the machines. Of course, we were doing many projects for noise reduction. One such is a tractor muffler silencers people use in the duct lines to reduce the noise, etc. I will again not go into details of noise control in this lecture, but just to give you an idea. But one most important thing we must know about this sound pressure level is the human auditory field. You will see everything here is a function of frequency. The speech when people talk is somewhere predominantly less than 5000 hertz. Music based on the membrane or bass instruments and the string instruments, they can go all the way from 50 hertz to about 12 kilohertz. Okay. And this is the threshold in quietness. It is not a linear level. Okay. And then the blue line is the list of damage risk. Okay. Limit of the damage risk. At high levels, we will have prolonged exposure of our ears to more than this level will create damage to our ears, and beyond these levels we will have a sensation of pain. So one has to be very, very careful, though the energy is insignificant from a thermodynamically speaking, thermodynamics point of view, but these levels are so damaging to our human ear that one has to be careful about. And as you can get a clue, our human ear is not at all linear, it is sensitive at different frequencies. Okay. So this is how the equal loudness contours for pure tones occur. We need to increase the sound pressure level at low frequencies compared to high frequencies to get the same sense of loudness or hearing. So that means our human ears hear a response to different sound levels differently at different frequencies, and for the same sound level they perceive differently at different frequencies. Okay. And this frequency response of a human ear is actually put in the measurements which we do with a microphone. For example, so this is, go to the next slide here. This, say for a 40 dB equal loudness contour, our human ear actually perceives it this way. Okay. So we hear, we have to increase the level to get the same perception. So this is actually our human ears, the green curve is actually the human ear's perception of any sound. Okay. So to account for that, we have developed what is known as this A weighting scale, which is universally adopted by we, I do not mean IIT Kharagpur, but everybody in the world. There are ISO standards. People use A weighting scale, okay, wherein to any measurement, suppose I had a microphone, I would have measuring this level, straight levels. So I will subtract certain values from these measured values at corresponding frequencies. Okay, when I come to frequencies, I will talk about certain filters. Okay. So this is what is known as an A weighting curve. Okay. So, any measurement which has been done in decibel and then corrected to A weighting is actually then represented in dBA. So, decibel in the A scale. There are of course B scales, C scales. These are used for higher levels. Actually, the international standard now is everybody represents SPL in dBA. Okay. And this is just nothing but an weighting scale, and these weights, A weights, is a function of frequencies. There are, you will see in many handbooks people have given equations for this A weighting, but then traditionally people had used filters. Okay. So, what is an octave filter, or what is an octave? Octave is nothing but 2 times f, twice the frequency is octave. A decade is 10 times frequency. So, if I have a signal in the frequency domain, a noise signal, and I try to put a filter around it, okay, this filter will have a low frequency, this will have a upper frequency, this will have the center frequency. So, center frequency is nothing but the geometry mean between FL and FU. Okay. So, if FU is twice of FL, this becomes what is known as an octave filter. If FU is 2 to the power 1 by 3 FL, this is known as a 1/3 octave filter. So, the grossly speaking, I have this audio band from 20 hertz to 20 kilohertz. If I stay, the first frequency is 125 hertz or maybe 63 hertz, okay, and this becomes 250 is the next octave band, 500 is the next octave band, 1000, because they are all doubling, 2000, 4000, 8000, 16,000. So, you see the entire audio band could be made out of such octave filter bands. For every such octave filter bands, if you look in the handbook, the A weighting values are given. You will be more in these low frequencies, and a good rule to remember is it is 0 at 1000 hertz. Okay. So, the value of SPL, suppose it is 90 dB at 1000 hertz, it will be also 90 dBA at 1000 hertz. And if you see predominantly, if your dBA for the same signal, dBA value is much less than dB, what can you say just looking at these two numbers? Anybody? This means what? Because you see here dBA values are much lower, because we have to subtract this amount. So, this is predominantly, and then particularly at high frequencies they are little more or almost equal. So, predominantly these signals are less than 1000 hertz. Okay. And let me tell you, in engineering noise control, many of the noise control issues are actually reducing this low frequency noise which is less than 1000 hertz. I will give you an example here. So, before coming to that example, so this is my linear scale dB lin. dB lin or dB, they are the same thing. Then I can have dBA scale, which we use throughout in the industry, and dBc is used for a 100 loudness curves, particularly when you're talking about aircraft noise. People talk about dBc and so on. Okay, and then frequency weighting are actually put in the sound level meter. So we have the microphone, we have preamplifier, this weighting curves, then we have an RMS peak detector and the integration time, whether it is fast, slow, impulse. And so for any signal, we get the number either in 87.2, it could be dB, dBA, dBb, dBc. So such sound level meters are available for noise monitoring of equipment. I just wanted to show you this. So this is the same blower which is being used in a steel plant to get fresh air to the blast furnace, because they have to be fed at a fast rate. So these blowers help in accelerating the flow of air into the blast furnace. And if you will predominantly see, this blower made a lot of noise, and when we went to the plant, this was around 110 decibels. It was very loud for any worker to stay around in this place. And if you will see, this spectrum which we have been measuring are actually represented in the 1/3 octaves bands, and this is predominantly the frequency is very, very loud. This is somewhere around 630 hertz, which happen to be the blower vane pass frequency, which gets modulated because of the other low frequency noises. So you'll see predominantly any noise control or noise monitoring you do, these are the low frequency noises one has to come across. Okay. So as I was telling you, if you can go to this iitnoise.com, you can see on our GYAN web resources 20 lectures on acoustics and noise control. And if you go to my book, you will see an example as to how we can find out the noise source in a refrigerator using the sound intensity probe. Thank you.